Dear viewers, today we are going to learn on enzymes under the course Food Microbiology. Biochemical changes in living cells are due to catalytic reactions that are regulated by the functions of enzymes. In living cells, enzymes catalyze hundreds of biochemical reactions that include degradation of macromolecules or nutrient molecules, conversion of simpler precursors to biological macromolecules, and transformation of several molecules to a different form. The study of enzymes is known as enzymology and has numerous practical applications in several areas. The term enzymes was first given by Frederick W. Kuhnke to molecules responsible for conversion of sugar to alcohol. In 1926, urease was the first enzyme isolated and characterized by James Sumner. Sumner found that the enzyme urease consists only of protein and postulated that all the enzymes are protein. In 1930, John Northrop and Moses Kunitz crystallized digestive enzymes including pepsin and trypsin and found them to be proteinaceous in nature. It was then confirmed that enzymes are proteinaceous in nature. Enzymes can be obtained from different sources such as animal, for example pepsin, trypsin and chymotrypsin, plant sources, papain and bromelain, and microorganisms, proteases, lipases, amylase, pectinase, chitinase, etc. Enzymes are very highly specific for their substrates and are central to every biochemical process. We will be studying about enzymes under the following subsections: general characteristics of enzymes, classification of enzymes, enzymatic reactions, enzyme kinetics, applications of enzymes in food industry, and lastly on the immobilized enzyme. Let's learn about general characteristics of enzyme. Enzymes are biocatalysts that catalyzes the conversion of a specific set of substrate into a specific product. During their participation in a reaction, the enzymes are neither consumed nor altered permanently. Enzymes are very effective biocatalysts which enhances the rate of reaction by a factor of 10 raised to power 5 to 10 raised to power 17. Unlike most of the chemical catalysts, enzymes are highly specific both for the single substrate or group of very closely related substrates and the type of reaction catalyzed by them. As most of the enzymes are protein, their catalytic ability depends on the integrity of the native protein conformation. Some RNA molecules also possesses ability to catalyze biochemical reactions and are called as ribozymes. If an enzyme is denatured due to external factors or degraded into smaller peptides or amino acids, it usually loses its activity. Some enzymes are completely made up of protein and do not require any functional group for catalyzing the reactions. However, other enzymes require a complex organic or metalloorganic molecule called coenzyme or chemical component called cofactor. Inorganic ions such as magnesium, zinc or iron. The coenzyme or the metal ion that is linked to the enzyme protein is called as prosthetic group, whereas the protein part of such enzyme is called as apoenzyme or apoprotein. The complete enzyme having catalytic ability is called as holoenzyme, which contain both apoenzyme and cofactor or coenzyme. Sum of the cofactor and coenzymes of specific enzymes is given in table 1. In terms of thermodynamics, the function of an enzyme is to reduce the activation energy for a reaction, enabling them to occur much more readily. Let's learn about the classification of enzymes. Enzymes are named by the addition of the suffix "ase" to the substrate name. Most of the enzymes catalyze the transfer of functional groups, electrons or atoms. Therefore, enzymes names are assigned according to their transfer reaction, the donor group or the group acceptor. According to International Union of Biochemists and Molecular Biology (IUBMB), enzymes are currently grouped into 6 functional classes, each with subclasses depending on the reaction they catalyze. The different functional classes and their biochemical reactions are given in Table 2. Each enzyme is assigned a systematic name and a 4-type classification number which identifies them. To know more on enzymatic reactions, any chemical reactions doesn't occur at the same rate and requires some energy for conversion of substrate to a final product. The enzymatic reactions are characterized by the formation of an enzyme substrate complex which takes place in the pocket of the enzyme known as active site. The active site of an enzyme contains amino acid residues which form a temporary bond with the substrate called as binding site, whereas specific residues that catalyzes the change in the substrate for the production of the specific product is known as catalytic site. The active site of the enzyme is composed of specific amino acid residues which forms the base for the binding of the substrate, resulting in the enzyme catalyzed reaction. Most of the enzyme substrate reaction are weak interactions between enzyme and substrate. Enzymatic reactions are mainly hydrogen bonds, hydrophobic bonds and ionic bond in nature. The chemical reaction of conversion of substrate S to product P form goes through a higher free energy state called the transition state. The transition state has the higher free energy in comparison to product or substrate as it is shown in the figure 1. The difference between the free energy of the substrate and the transition is known as the activation energy or the Gibbs free energy of activation. The function of an enzyme in a chemical reaction is to lower the activation energy or to facilitate the transition state formation as depicted in figure 1. Let's learn about the factors affecting the enzyme activity. There are several factors which affect the activity of an enzyme, which includes number 1, enzyme concentration, number 2, ligand concentration, that is substrate product and inhibitor concentrations, number 3, pH, acidity and the basicity that is, and number 4 or lastly the temperature. The activity of an enzyme increases with the increase in temperature until the optimum temperature beyond which the activity of the enzyme reduces. The temperature or pH at which the activity of the enzyme is the maximum is known as optimum temperature or pH. Apart from these factors, presence of activators, inhibitors and cofactors can also affect the activity of an enzyme. Enzyme inhibitors block enzyme activity by several mechanisms. Activators enhances the catalysis, whereas cofactors are necessary for normal enzyme activity. Let's learn about enzyme substrate reaction. Enzyme substrate reaction is generally explained using two models. Number 1, lock and key model, and number 2, Koshland's induced fit model. In lock and key model of enzyme substrate binding, the active site of the free enzyme is complementary in structure to the substrate, as depicted in figure 2a. Thus, the substrate easily binds to its specific enzyme and forms an enzyme substrate complex. In case of Koshland's induced fit model, the formation of the enzyme substrate complex is the result of the specific interaction between the substrate and a flexible active site of the enzyme. The binding of the substrate results in the conformational changes in the enzyme, making it complementary to the enzyme as shown in figure 2b. To know on enzyme kinetics, during an enzyme mediated chemical reaction, the substrate is converted to a product. A simple enzyme substrate reaction for the formation of product can be written as shown in the equation 1, where E represents the enzyme that catalyzes the chemical reaction and S represents the substrate which undergoes the changes, and P the product formed as the result of the reaction. For understanding the function of an enzyme, a biocatalyst, we should understand first that the function of a catalyst is to increase the rate of a reaction. The catalyst does not affect the reaction equilibria. Michaelis-Menten equation. Michaelis-Menten equation is one of the most important equation in enzyme kinetics, derived by German biochemist Leonard Michaelis and Canadian physician Maud Menten. The equation was derived based on the basic hypothesis that the rate limiting step in an enzyme catalyzed reaction is the conversion of the enzyme substrate complex ES into the product P and free enzyme. The Michaelis-Menten equation is given below as equation 2. In this formula, VO represents initial velocity, Vmax represents maximum velocity, S represents concentration of the substrate, and Km represents Michaelis constant. The Michaelis-Menten equation assumes a two-step enzyme catalyzed reaction. 1. Binding of enzyme and substrate to form an enzyme substrate complex, and number 2. Catalyzes where the product is formed and released from the complex. The equation suggests that the initial velocity of the reaction depends on the substrate concentration and Km. Vmax reveals the velocity of the enzyme at saturating substrates concentrations. For a normal enzyme substrate reaction, K1 signifies the rate constant for the formation of enzyme substrate complex after the reaction between the enzyme and the substrate. As the reaction is reversible, the dissociation of enzyme and substrate from the enzyme substrate complex has a rate constant K minus 1. However, if the reaction proceeds from enzyme substrate complex to the formation of the product, the rate constant is denoted as K2. The proposed model is given in the equation 3, wherein Km is defined as a Michaelis constant, which is derived as the ratio of the rate constant as shown in the equation 4. Km values of most of the enzymes vary between 10 raised to power 1 and 10 raised to power minus 7, and the value depends on specific substrates and factors such as temperature, ionic strength and pH. Also, Km signifies the concentration of the substrate, which occupies half of the active site of the total enzyme concentration. Km is equal to K raised to power 1 plus K2 divided by K1. This is the equation number 4. The units of enzyme activity. Enzyme activity is expressed as unit activity, total activity and specific activity. A unit activity of an enzyme is defined as amount of specific enzyme responsible for conversion of 1 micromole a specific substrate to a final product per minute under a specific set of conditions. The concentration of an enzyme is referred in terms of milligrams or micromoles. Total activity of an enzyme is defined as an activity of enzyme per ml of the extract. Specific activity of an enzyme is defined as unit activity per milligram of protein and represented as micromole per milligram per minute. Specific activity is constant for a purified enzyme at a given set of conditions. Concentration of an enzyme calculated in microgram per ml can be converted to molar units by dividing the value by the molecular weight. Turnover number. Turnover number or kcat of an enzyme is defined as the number of substrate molecules converted to a product by one enzyme molecule per second. For example, if turnover number of carbonic anhydrase is 4 multiplied by 10 S or S raised to power minus 1 means that each molecule of carbonic anhydrase produces 4 lakh molecules of the product per second. The turnover numbers of most enzymes with their physiological substrates fall in the range from 1 to 107 per second. Turnover number of acetylcholine esterase is 3 multiplied by 107 per second, which is one of the highest among the enzymes. When the concentration of the substrate is much higher than Km value, the rate of catalysis is equal to turnover number kcat. Let's learn about the applications of enzymes. Apart from role of enzymes in several cellular activities, they have practical applications in many industries including food, pharmaceutical, baking, brewing, flavor, color, textile, biofuel and tannery industry. Depending on the kind of process, the type of enzyme is selected as enzymes are very specific to their substrates. Proteases and lipases are one of the important enzymes in leather industry for the removal of proteins and fats respectively. Proteases, lipases and amylases are one of the important components of the detergent for the removal of hard stains. Application of specific enzyme in different industries is given in table 3. Apart from applications in several industries, enzymes have been used in therapeutic and medical applications. Enzymes such as streptokinase has been used to remove blood clots, which reduce the risk of cardiovascular diseases. Enzymes such as papain are orally administered after the food for easier digestion in old geriatric patients. In pharmaceutical industry, enzymes are used for the production of antibiotic and kits for the diagnosis of specific disorders. Enzymes such as amylases, lactases, cellulases and pectinases are used in food industries with specific applications as depicted in table number 4. The biotechnological method of producing enzyme is expensive, and hence new methods have been implemented to reduce the cost. In order to make the enzyme work efficiently and to reuse the enzyme, the new technology known as immobilization or captured has been implemented. Immobilized enzyme is defined as cells, alive or dead, or enzyme anchored to a solid support for use in bioconversion. Such enzyme helps in reducing the washout rates and increases the turnover rate. This in turn decreases the cost of the enzyme and increase the efficiency of the enzyme reaction in food, pharmacology, environmental management, industries and in other allied industries. Such immobilization helps in stabilization of enzymes and restricts the cross reactions. This would result in the restriction of unwanted metabolite production, thereby ensuring the product purity. Let's learn about the methods used for the immobilization of enzymes. Immobilization of enzymes fall into four main categories. Number 1, physical adsorption onto an inert carrier. Number 2, encapsulation. Number 3, cross-linking of the protein with a bifunctional reagent, and number 4, covalent binding to a reactive insoluble support. Let's learn about physical adsorption method. Physical adsorption of an enzyme onto a solid is probably the simplest way of preparing immobilized enzymes, figure 3. The method relies on non-specific physical interaction between the enzyme protein and the surface of the matrix brought about by mixing a concentrated solution of enzyme with the solid. The second method is encapsulation. Confining enzymes within the lattices of polymerized gels is another method for immobilization, which is called as encapsulation, as depicted in figure 3. This allows the free diffusion of the low molecular weight substrates and reaction products. The usual method is to polymerize the hydrophilic matrix in an aqueous solution of the enzyme and break up the polymeric mass to the desired particle size. The third method is on cross-linking. Immobilization of enzymes has been achieved by intermolecular cross-linking of the protein either to the protein molecules or to the functional groups on an insoluble support matrix. Cross-linking an enzyme to itself is both expensive and insufficient, as some of the protein material will invariably be acting mainly as a support, resulting in relatively low enzyme activity. Generally, cross-linking is the best used method in conjunction with one of the other methods. The covalent binding method. The most intensely studied insolubilization technique is the formation of covalent bonds between the enzyme and the support matrix. When trying to select the type of reaction by which a given protein should be insolubilized, the choice is limited. Limitations are due to the fact that the binding reactions must be performed without loss of enzymic activity, and the active site of the enzyme must be unaffected by the reagents used. A small number of reactions have been designed to couple with functional groups on the protein other than the amino and the phenolic residues. As with the cross-linking, covalent bonding should provide stable insolubilized enzymes, derivatives that do not leach enzyme into the surrounding solutions. The wide variety of binding carriers with functional groups capable of covalent coupling or being activated to give such groups makes this a generally applicable method of insolubilization. Chemical groups in the support or carrier that can form covalent bonds with support are amino groups, imino groups, hydroxyl groups, methyl thiol groups, carboxyl groups, guanidine groups, imidazole groups, thiol groups, and phenol rings. Figure 3 depicts types of techniques used for immobilization of enzymes. The advantages of the immobilized enzyme. There is increase in functional efficiency of the enzyme along with enhancement of reproducibility of enzyme catalyzed process. The immobilized enzyme can be reused and the process is continuous with less labor involved. Number 3, Due to reuse of the enzyme, the capital cost and investment during the process is reduced. Number 4, this is a controlled process and there are less chances of contamination. Number 5, there is more stability of the product due to the improved process control. To conclude on enzymes, enzymes are biocatalysts which are important for all the biological reactions. These reactions may be for the release of energy required for all the cellular activity like metabolism, repair of cells and the organelle, reproduction and degradation of toxic compounds. Enzymes are widely used in several industries such as food, pharmaceutical, flavor, color, textile, biofuel and tannery industry. In food industries, enzymes are fast replacing the inorganic reactions so as to decrease the pollution caused by chemicals which otherwise would have been used in food industries. In recent years, enzymes are applied in food industry for the hydrolysis of macromolecules, for the production of metabolites with higher health benefits. Thank you, viewers.